Hey guys, this is Stef from Samayas and welcome to my channel. Today I'm going to go deep into the BIOS setting of the 13th Gen Dell servers. For this I'll be using a Dell R630, but they're more or less the same for all other servers of the same generation. So let's dig in. So let's start up this server and see what the boot screen shows us. It shows us it's a Dell PowerEdge R630. It shows us the BIOS version, which is 2.19.0, and it will show us the iDRAC IP address, which we are already connected to right now. Servers like these always take quite a lot of time just to boot up. Loads of installation to be done and loads of checking. Now it gives us 4 options: F2 for system setup, F10 for lifecycle controller, F11 for boot manager, and F12 for PXE boot. Let's go into system setup. In the meantime, it shows us the IP address, which is 192.168.150.59. So here first we have the system setup, BIOS settings, we have iDRAC settings, and we have device settings. So when you look at this BIOS, this is a full text BIOS. Compared to the other one, which is full GUI, this PowerEdge R730 XT stays always in text. Whatever I do or try, nothing changes. It's at the latest BIOS, I can't update anything anymore. According to AI, on some models this happens and there's no way to fix it. So you still might have a full text other than a full GUI, but other than that, everything else is the same. So let's go into the BIOS settings. So on the bottom we have a service tag, which is always handy if your system is still in support. This one isn't, of course. Let's have a look at the system information. Again, the tag, our system CPLD, the UEFI version, whom it's from. Next, let's look at the memory settings. As you can see, it has 128 GB of memory on 2133 MHz. System memory testing is disabled, and I've used the default configuration, just the optimizer mode. So let's dig in a little bit into the memory operating mode, because that immediately impacts the available memory or the speed of your memory. So basically, the 13th Gen Dell servers have 7 memory modes. The first memory mode is called optimizer mode, and that's a default. You have 128 GB of memory available, which is full memory capacity at max performance. There's no redundancy beyond ECC. This is the best mode for speed. The second memory mode is called the advanced ECC mode. You still have 128 GB of memory available. We have full capacity with enhanced ECC. It corrects single-bit errors and detects some multi-bit ones, which is great for enterprise environments. The third memory mode is called the spare mode. You only have between 96 GB and 112 GB of memory available. So a portion of the memory is reserved as a hot spare rank. If one rank fails, it switches over. You do lose some memory. The fourth memory mode is called the mirror mode. This is the worst. You only have 64 GB of memory available. So memory is mirrored across DIMMs, meaning only half is used for redundancy. The fourth memory mode is called the mirror mode. This is the worst. You only have 64 GB of memory available. So memory is mirrored across DIMMs, meaning half is used as redundancy. This is great for mission critical systems. The fifth memory mode is called the spare plus advanced ECC mode. It's a combination between the third spare mode and the second advanced ECC mode. You have again between 96 GB and 112 GB of memory available. There's a trade-off between capacity and tolerance. The sixth memory mode is the fault resilient mode. You have between 120 and 124 GB of memory. We have a small portion which is reserved for the hypervisor kernel, like Proxmox, VMware or Hyper-V. This is useful for virtualization stability. The final, 7th memory mode is called the NUMA fault resilient mode. It's the same one as the fault tolerant resilient mode, but with some NUMA node. This is perfect for systems with dual CPUs and NUMA-aware hypervisors. So as you can see, for the memory operating mode, I chose optimizer mode. I chose for maximum memory and maximum speed, and at this time I don't really need the extra bells and whistles. The next option is node interleaving. If this option is enabled, the 128 GB of memory is available across all CPUs. If this option is disabled, like this, right now, the first CPU has 64 GB of memory and the second GPU also has 64 GB of memory. In essence, most modern systems like Proxmox and VMware and Windows Server 20X does support NUMA and don't need node interleaving anymore because they handle themselves. This is more something for the older systems, aka Windows 2008 and lower. The last option is Snoop modes. Snoop modes manage coherent cache management between multiple CPUs in a multi-system CPU, like this one. How and when processor will check each other's cache for the latest data. They balance between latency, bandwidth efficiency and scalability. Again, I chose early snooping, which is the fastest option. Next up, let's look at the processor settings. The most important part on this page is at the bottom. What are the processors in my system? And here we have two Intel Xeon E5 2680 V4 CPUs. If you go back to the top, first we have the flag logical processor. A logical processor creates us a second virtual processor for each physical processor. In most modern day systems, there is no need to disable this. It's only certain very old legacy systems that might still require them. And since this is already a pretty old system, I don't think there's still any use for that. The next two lines, QPI speed and power management, QPI stands for Quit Path Interconnect, which determines the speed between the CPU and the memory. In general, we should leave it on enable and maximum data rate. It's only in situations where we want to lower the power usage of the system that we might lower the speed. And then we also need to lower the memory speed. The alternate request transaction ID is something which allows transactions between CPUs to be highly optimized in combination with NUMA. But then again, NUMA these days is handled by the hypervisor itself, and so this option should stay disabled. The virtualization technology VTX is something which is required for hypervisors aka VMware, Hyper-V, Proxmox, etc. The address translation service works with Intel VTD to let PCIe devices translate virtual memory addresses. This is very useful for direct access from the hypervisor to physical PCIe device. The adjacent cache line prefetcher prefetches the next cache and so should presumably augment the performance of the system. The hardware prefetcher. The CPU automatically tries to detect certain patterns and preloads memory into cache. This again should augment the performance, and so it's enabled. The goal of the DCU streamer prefetcher is to reduce wait time for memory reads in streaming workloads, aka video decoding, matrix optimizations, etc. The DCU IP prefetcher tries to improve performance by prefetching data that typically might be missed from cache. Logical processor idling decides whether or not your hypervisor has access and can shut down logical processors and/or reduce power usage and heat. On high-performance systems, aka real-time systems, this should be disabled. On other not-so-heavy loaded systems, this can be enabled. Configurable TDU stands for Thermal Design Power. So in essence, here you can control whether or not your CPUs will use their max power, or if you choose level 1, whether they might be reduced to 10 to 20%, which means less power, which also means less speed and less performance. That depends on your need. The X2 Epic mode enables extended X2 APIC for advanced interrupt handling. In general, on most multi-socket, multi-core systems, that should be enabled. It's only for older hypervisors that should be disabled. The Dell controlled turbo option, which is disabled by default, allows you to overclock your CPU. If you look at the options, we have 3 what they call bins, which means a first bin means you will overclock by 100 MHz. A second bin means you will overclock by 200 MHz. And a third bin by 300 MHz. That means more power usage, more heat, but also more performance. And it's up to you whether or not you want to enable that or disable. Next up, we can also limit the number of cores available on the CPU. My CPU currently has 14 cores, and so technically I could decide to only use 1, 2, 4, 6, 8, 10 or 12. So why would I limit the number of cores on a processor? Well, the first reason is power and thermal issues. Say you have a limitation in power available, or your server in the location where it's located is producing too much heat. By lowering the number of cores, the heat will go down. A second reason might be licensing costs. Say you have a Windows or a SQL server which is only licensed for X number of cores. Disabling the extra cores will keep you compliant. The next step is NUM optimization. However, for Proxmox and VMware, since it's handled inside the OS, it doesn't really play. Now let's have a look at the SATA settings. If you come on a SATA screen, the first thing you notice is the number of ports. If I count correctly, I have from port A all the way up to port G, and that's 10, even though my system only has 8 ports and or drives. If you look at the embedded SATA option mode, we have 3 different types of mode. First, we have the ATA mode, which is the really old mode. ATA stands for Advanced Technology Attachment. It's for legacy purposes. It does not support hot swap or native command queuing, and it's only for old OSs like Windows XP. The second mode is the AHCI mode, or the Advanced Host Controller Interface. It supports modern SATA drives, it supports hot swap, native command queuing for SSD drives, and trim for SSD drives. And it's more or less the mode which is run without RAID. And the last mode is the RAID mode. If you put it in there, in essence, your whole configuration is transferred to a per controller. In my current situation, I have 1 TB SSD drive and 4 1.2 TB SAS drives. And in my current configuration, I chose to use the AHCI mode and to pass each individual drive to my Proxmox, even though I have a config. Now let's have a look at the boot settings. In here we have 2 modes. We have the BIOS mode or the UEFI mode. BIOS stands for Basic Input Output and is the old classical way. UEFI stands for Unified Extensible Firmware Interface and is the more modern way. Most modern OSs like VMware, Proxmox, Ubuntu do support UEFI, so it's best to use UEFI boot sequence. If we look at the UEFI boot settings, here we can determine the boot sequence on which the system will boot. As you can see, there's 4 options. The bottom 2 are the disks which are available. I have an internal USB drive and I have an external USB drive. And on those, on the internal USB drive, there's Proxmox, and on the external USB drive, there's a Debian installed. Let's look now at the networking settings. First, as you can see, the system detects 4 devices. I have a LOM with 2 RJ45 ports and 2 SFP+ ports. Currently, each of those devices are disabled for PXE boot. If I click on Enable, I can configure individually how a PXE boot should work. I can choose the interface on which it should work. I can choose whether or not I use protocol IPv4 or IPv6, and or I could configure extra LAN, VLAN settings. I'll disable it again. And the second part, I could also configure an iSCSI initiator name. If I enable it, I have extra iSCSI settings, and instead of having a system with local disks, this system could run completely from the BIOS on an iSCSI device, somewhere on another server. I have the possibility to have one or more connections for speed, enable 1, enable 2, and it chooses the connection order, and in each of those connections I can choose which interface to use, again what protocol, IPv4 or IPv6, whether or not I have a VLAN, whether or not it's DHCP enabled, and CHAP in case I need to authenticate my iSCSI device. Let's disable it back. Now let's have a look at the integrated devices. First, we have the option to enable or disable USB 3 settings. I have enabled them since I'm using my internal USB drive to boot my system. The second option allows me to enable or disable all USB ports. I can enable them all, I can disable them all, or I can just enable the backend USB ports. If I disable them all, even a keyboard and mouse won't work. But in some environments where you need to be totally secure, it's maybe a good thing to disable all ports and only allow access through iDRAC. The next one allows me to enable or disable the internal USB port. I have enabled it since I'm using it as a boot drive. Next, we are able to enable or disable the internal RAID controller. Even though I'm not using RAID at this time, it's still enabled. We could also enable or disable the integrated networking card. Suppose you have added extra networking cards and you don't need the internal one, you can disable them. Then we have the IOAT-DMA engine, which is an acceleration engine which is mainly used for 1 GB cards. Since my device is connected through an SFP Plus port, I have disabled it. So the IO non-posted prefetch is a low-level performance tweak which allows the CPU to handle I/O transactions specifically for PCIe devices like network cards, storage controllers and GPUs. Since I'm using SFP+, it's advised to have it enabled, so it's enabled. The next one is I/O snoop hold-off response. It's a BIOS setting which affects CPU delay snoop responses during I/O operation. It's again a tuning option in charge of impacting balance between CPU, memory and I/O latency. Snoop refers to the CPU checking other caches to maintain memory consistency. So the I/O snoop hold-off response is again a tuning option. It changes the impact between the CPU memory performance and I/O device latency. Snoop refers to the CPU checking other caches to maintain memory consistency. The hold-off response introduces a delay in nanoseconds or cycles before the CPU responds to I/O snoops. Delay helps prioritize I/O traffic over frequently memory snoops, reducing I/O latency. I currently have it as 256, which is the more balanced use. 512 is good for a lot of I/O workloads. 1K is good for VM traffic and more heavy I/O workloads. And 2K is for very heavy storage servers. Maybe I should switch it to 1K, but currently it's running at 256. Next is the embedded video controller. If your system does not have any other video controller inserted, disabling will completely disable the output of any video output. That means you won't see your BIOS screen anymore. This also means that the way I'm using right now my iDRAC to see my boot system settings, it won't work either. So be very careful when disabling it. Next we have the SR-IOV Global Enable. This allows PCIe devices, for instance NICs storage controllers, that support SR-IOV to create virtual functions. These virtual functions can be assigned directly to virtual machines, for instance in Proxmox or VMware, using PCIe pass-through. This gives the VM direct access to device resources for high-speed applications. Since I currently have no requirements for that, I have disabled this option. Next, we have the OS Watchdog Timer. It will monitor I/O operations, it will detect timeouts, and it will respond with a system reset and/or with alerting. If you have systems like database systems or virtualizations which have critical I/O operations, you should enable it. Since this is a testing environment and I don't want the system to reboot, I have disabled it. So memory mapped I/O above 4 GB. Memory mapped I/O above 4 GB. It refers to the ability of a system to map certain I/O addresses above the 4 GB memory limit. This is mostly a feature related to 64-bit system, allowing them to access more of the 4 GB system of memory and I/O resources. Normally, 32-bit systems are limited to 4 GB addressable memory, but 64-bit systems can access much larger amounts of memory, including above 4 GB. So why does it matter? These days, all systems are 64-bit. The above 4 GB region is used to allocate space for I/O devices and higher memory operations. It provides high-capacity storage arrays, advanced GPU, mixed with advanced SR-IOV functions. The lower memory mapping I/O base to 512 GB. This will force the I/O mapping on one side to go above 4 GB, but on the other side to stay on 512 GB. I have disabled this option since my system doesn't have more than 512 GB, but in systems which have 1 TB or more, this might be something that should be activated. The next option is slot disablement. So if we really want, we can disable a number of slots. The global slot boot driver disablement, I have disabled it, but should I enable it, will disable the possibility to boot from a PCIe device or a networking device. Then I have enabled slot 2 since I currently have a GPU in the system. Next we have slot bifurcation. Currently I have not switched bifurcation because I'm not really using it. Bifurcation is specifically used for PCIe devices, for instance, where you have one device on which you put 2 or 4 external M.2 drives. And if you don't have the bifurcation option, the system will only see one M.2 drive. Here we have the option for 4x4x4x4 bifurcation or 8x8 bifurcation, depending on the card. In this system, I'm not using it. Now let's look at the serial communication. This device still has a serial port. Here we can enable or disable the serial port and how it should function. We have on with console redirection, we have the auto mode, we have on with console direction via COM1 or via COM2, or we have it off. Since I'm not using it, I simply disabled it. And we can choose whether or not we have device 1 as COM2 and device 2 as COM1, or vice versa. We can also choose whether to use serial device 1 or 2. And we can choose the baud rate and the terminal mode type, ANSI or VT100, VT200. And we can redirect after boot, which is enabled or disabled. Now let's have a look at the system profile settings. Here we can really tweak the power usage, the heat it produces, and the noise it makes. We have currently 5 profiles. I chose the performance per watt, the APC, which returns me a maximum efficiency for a reasonable noise and a reasonable power usage. The second one is the performance per watt but OS controlled, which is still optimized energy efficiently wise, but the OS has some controls in it. The third one is the really performance one. If you have a high performance database or real-time processing system, you will choose that one. The next one is a dense. If you have like a 42 rack filled with those 1U R630 servers and heat and power consumption becomes an issue, you will choose a dense profile. It will lower a little bit of the performance, but it will also lower the heat and the power usage. And the last one is the custom, where you can tweak yourself individually each of those settings. In system security, as the name says it, we can secure the system. The first two is we have a system and a setup password. If we enter a system password, every time we boot, we'll have to enter that password or the system won't boot. We have a setup password, which will just secure entering the BIOS settings. Then we have a password status, whether or not it's locked or not locked. The next one, we can enable or disable the power button physically. If we disable it, there's no way of powering on the machine physically. You will need to do it through iDRAC. The NMI button is something which is mainly used by Dell engineers and shouldn't normally be used, so I've disabled it. The AC power recovery defines what will happen after a system loses power and then receives power again. Should it power on automatically? Should it stay off automatically? Or should it stay in last mode? If it was on, it powers on again. If it was off, it stays off. And then associated with that, we have the AC power recovery delay to decide whether or not, when the system receives power again, to immediately power on or to use a user predefined time or a random amount, not to avoid for having your electrical grid in overload. Next off, we have UEFI variable access. In standard mode, once booted, your OS can tweak all UEFI settings. In controlled mode, your system can only read certain settings and can't modify anything. Next up, you have a secure boot. I currently have disabled secure boot since I want to tinker around with different ISOs, OSs, etc., and not all of them are signed. However, if you are running VMware, Hyper-V or Proxmox and only that, enabling secure boot is maybe a better choice. And finally, we have a secured boot policy. Depending on whether you choose standard or custom, in the standard you just have the predefined and preloaded certificates to allow certain systems to boot or not. If you go to the custom, you could also load your own keys to tweak it. And finally, we come to miscellaneous settings. A little bit of everything. We can see the time, we can modify it, we can give it a specific asset name, we can specify whether or not F1, F2 prompts an error, we can enable or disable the numlock key, we can load legacy BIOS ROM or not, and we can enable or disable in-system characterization. So this completes more or less the system BIOS settings. Now let's look at the iDRAC settings in the BIOS. So here again we first can see the BIOS version. We have a summary on which system is running, which version is running, etc. The IP address, the configuration, the backplane version, etc. We can see specific errors, should there be any. We can also clear the records. Currently we have 37 warnings. I can clear them. Then we have the iDRAC networking settings. If when you first receive this device the networking settings are hard-coded IP address or don't correspond to your network, by going in here you can choose whether or not you want to have a static IP, a DHCP address, etc. You could also choose whether or not you're using the dedicated network card or whether or not you want to use one of the other LOMs in the system. You can choose whether or not to have auto-negotiate on or off. You can hard-code it if you want. You can register the DRAC already in the DNS if you want. You can give it a name. And you can choose whether or not you want to auto-configure the domain or not. And then you either hard-code the IP address or you use DHCP. You choose whether or not to have IPv4 or IPv6. And you configure a number of DNS servers. And you can also enable or disable the IPMI settings, which allows you to configure it through a specific tool as well. Next we have the alerts. Whether or not your iDRACs should send out alert messages. An alert will be generated if there's a power loss or restoration, if a fan is overheating or failing, if a drive is failing, if we have CPU or memory or PSU errors, or if the system reboots, shutdowns or crashes. We can specify an IP address and it will send out SNMP trap, or via email or via a syslog. Now let's have a look at terminal. Here again I can choose which terminal profile this server is running on. Default terminal profile, maximum performance, minimum performance. This terminal profile works in conjunction with the previously seen system profile. And here again we can decide whether or not we allow 70 degrees or only 55 degrees. Or only 50. Depending on the maximum, the higher the temperature, the lower the fan speed can be. The lower the temperature, the higher the fan speed and the noise will be. Since I don't mind the extra temperature but I prefer to have less noise, I chose 70 degrees. We can also use a fan speed offset to lower or higher the fan speed. Next, should we have multiple servers in multiple data centers across multiple racks, etc., here we can specify the location of the data center, the location of the aisle, of the rack, of the slot, etc. And finally, we have the user configuration. Here we can do a reset, specify which is the username, and change the password should we have forgotten it, and or override it. That's why it's maybe very important to have a system BIOS password, because if somebody has physical access to this machine but doesn't necessarily know the iDRAC settings, by going in here, you can just reset it. Next, we have the iDRAC user configuration. Here, we can enable or disable a user. We could change the username, we can change the password, we can specify the privileges. For instance, a serial port user could have certain accesses or could be completely disabled. A LAN user could have administrative access, could have operator, or only user, which is read-only. That's why it's very important to also have a BIOS password. Because if somebody doesn't have remote access but has physical access to the machine, he can just reboot the machine, change this password, and then have full access to the machine remotely. Of course, if good monitoring is in place, you will detect that the server has been rebooted. But still, the next option is smart card access. Here we can enable or disable whether or not the system will use smart card to authenticate the user to have access to certain things. Next, we have communication permissions. Here we have an option to allow the OS to iDRAC whether pass through a LAN or through USB NIC. I will do a different video on that one. If you have like a full park of servers, the auto discovery option allows you to one time create a configuration file, and the moment the system boots up, it will reconfigure the way you want by default each of those iDRAC settings for each of the servers, which in a bigger setup is quite handy. And then finally, last thing, should you have fucked up for whatever reason your iDRAC settings, here you can do full reset and everything will come back to basics. Now let's have a look at the device setting. First, we see the HBA mini controller. Then we see 4 network cards which are on one LAN. Let's have a look in the HBA mini controller. First we see the latest version. Then we have controller management. We see the controller, the version, etc. We have certain options we can enable or disable. We can enable legacy BIOS. Instead if you need to boot for an older system, which is not the case, so it's disabled. And then I have the physical disk management. I can view all the disks it recognizes. As you can see, I have 5 disks in the system. The first is the SSD drive, and the next 4 are the SAS drives. And I have specific operations I can execute on those. I can have it blink to find which drive has causing the issues and what I can do with it. And that's about it. So this is a basic controller that does not allow anything more than just accessing SAS drives other than SATA drives. Out of the box, the R730 supports only SATA. If you want to have SAS drives as well, we need an HBA or a PER controller. And here I've inserted an HBA A330. Next, let's go to the networking cards. I can see the firmware up version. I have NIC configuration, whether or not I support legacy PXE boot or not. I can enable or disable the wake on LAN. I can configure a VLAN ID and an LLPD agent. I can also here configure specifically iSCSI, which is also something we can do in a normal interface. I have not played with this, so I don't know which takes precedence on which and where we need to do it exactly, but I'm sure going to do that in one of the future versions. Here we can specify the IP address, the iSCSI name, the CHAP ID and secret if needed. And finally we can specify virtualization mode, whether or not it's a normal card or we use SR-IOV functions. Currently it's at none, and that is the same for all network cards. Now let's have a look at the RAID 5 PERC H730 controller on my Dell R930. Let's first look at the configuration management. I can view the disk group that I've created. Currently I have 1 full RAID 5 partitions with all my disks. I could clear configuration if I choose to restart. I can see my controller management. In here I have a little bit more details about the firmware and the settings of my RAID PERC controller. And I have 2 advanced menus. I have the advanced controller management and the advanced controller properties. First I can choose to clear any error events, should there be any, or I could save them somewhere. I could save debug log. Next is the enable security. This allows me to encrypt the disks if I need to. Let's click on it. Currently the only option I have is to only save the key on a local key management inside the PERC controller. This is fine for now, but if the local PERC controller gets destroyed, is faulty, I can't recover my disks anymore. So this is something to keep in mind. Let's continue for now and click OK. At least here we have the flexibility to enter a security key and a passphrase. So as long as we save those information clearly, afterwards, when putting in a new Pro controller, we can still recover the disks. For now, I won't do that. Should I have enabled the security, I also have an option to disable the security, and I also have an option to change the encryption key. Next, I have my manage link speeds on my controller. My system has a possibility of 32 drives. However, I only see 8 physical controllers, from 0 to 7. That means that I control the speed per 4 disks on the system. Now in general, everything needs to stay on auto. This is only necessary if in this system you would put in older SATA 1 or 2 or 3. The autos in general means 12 GB. We could lower it to 3 GB, to 6 GB, or to 12. Finally, we have the option to reset everything back to the default settings, or we can switch the system to an HBA mode. In HBA mode, there's no RAID and each disk is individually passed to the host system. For instance, to a Proxmox who wants to do things themselves, or to a true NAS. Next to advanced controller management, we also have advanced controller properties. In here we can clear the cache, should we choose to. We have patrol read. Patrol read is a background operation that scans the drive in a RAID array. It proactively detects and fixes potential issues. Think of it like a scheduled health checkup, but for RAID drives. It reads the entire surface of a disk and looks for bad sectors or inconsistencies. If it finds something, it can trigger a recovery mechanism or mark a disk as failed. This is especially useful for RAID 5 and RAID 6 configurations. For now, I won't do anything. And we have the physical disk power, the same thing as the power management we already seen somewhere else in the BIOS. If your system has only a limited amount of power, instead of no power savings, we can go to balanced power mode, max power saving, or custom power settings. Finally, we have a spare option. Currently my system is in RAID 5, which in essence already has a spare per I don't know how many bytes. However, by configuring a spare, we could have a separate disk which is just ready in case another disk fails in a volume, and then assign it. In a system like this with 32 spaces, it's possible. In smaller system, it's less feasible. And finally we have task RAIDs. These are all the background processes like background intelligence RAIDs, like consistency check, like rebuild RAID and reconstruction RAID. By default, they're configured at 30%. Depending on the load of a system and or the tasks you want to start in background, you can put it all the way to 100% for your system to recover faster, or all the way to 0 to pause everything. My disk cache is configured to default. Should my system be completely in non-RAID, I can also choose to enable or disable it. I can import foreign configurations if I move my disks from another system to these systems. And on boot mode, I can choose whether or not to stop on error, to pause on error, to invoke the errors, or to save mode on errors. What is T10PI? T10PI adds an extra metadata protection information level on each block, which is typically between 512 and 4K at disk and controller level. It helps silent data corruption, misdirected writes, and data loss due to cabling or firmware issues. Now in this system it's disabled. It only works when your controller is in HBA mode and not in RAID mode. And my system is in RAID mode. The next section is board consistency checks on error. Since it's just a server to play around, I disabled it. In production, it should rather be enabled. And then finally we have the non-RAID disks mode. Should we have any disks also in the system which are not in RAID, if we enable this, they will be passed through to the host OS. If you go to virtual disk management, I only have one RAID configuration, which we see here, and there we can have a number of operations on it. We can make it blink. It's easy to identify all the disks in a specific volume. We can unblink. We delete the configuration and or reconfigure the virtual disk. We can see the assigned physical disks to this volume, and we can configure the read and write caches for each of the volume. And finally we have hardware components. We can see battery details, and we can see where the enclosure is located and which are the disks under the enclosure, should we have more than one power controller in the system. And that's it for the power controller. So this is the overview of the device. This concludes the in-depth review of the Dell 13 Gen series BIOS settings. I've based this video mainly on the Dell R630, but there are also some Dell R730 XT text BIOS details as well as a RAID controller, which is located in a Dell R930. The Dell R630 and R730 and R930 are quite comparable, with some minor details and some changes about processor, memories and ROM. I'll also be doing a review about the lifecycle controller in another video. If you like this content, give it a thumbs up. Don't forget to subscribe to this channel and press the bell sign. Or leave a comment down below.